Recently, China's experimental advanced superconducting tokamak achieved a peak temperature of 288 million degrees Fahrenheit, which is over 10 times hotter than the sun. The latest feat by the Chinese scientists is a significant step in the country's quest to unlock clean and limitless energy with minimal waste products. The experimental advanced superconducting tokamak reactor is an advanced nuclear fusion experimental research device located at the Institute of Plasma Physics of the Chinese Academy of Sciences in Hefei, China. The purpose of the artificial sun is to replicate the process of nuclear fusion, which is the same reaction that powers the sun. Now, how does this fusion thing work? Nuclear fusion is the reaction that occurs at the heart of the sun, generating potentially limitless amounts of energy. It works by combining two atoms into a single one. When this happens, massive amounts of energy are released. Our sun fuses hydrogen atoms into helium at a rate of 620 million metric tons a second, creating the light and heat we all need to survive. While the concept of nuclear fusion has been around for almost 100 years, we have never been able to generate enough energy to successfully replicate the process in a sustainable and safe way. However, it seems that China is on the verge of harnessing the energy from the nuclear fusion reaction for the first time. So, how a tokamak device achieves this nuclear fusion? The tokamak is an experimental machine designed to harness the energy of fusion. Basically, the hydrogen gas, when heated to very high temperatures, changes from a gaseous state to the plasma state, in which the negatively charged electrons are separated from the positively charged ions. Normally, fusion is not possible because the strongly repulsive electrostatic forces between the positively charged ions prevent them from getting close enough to collide and for fusion to occur. However, if the conditions are such that the ions can overcome the electrostatic forces, they can come within a very close range of each other for the fusion to take place. Such conditions can occur when the temperature increases, causing the ions to move faster and eventually reach speeds high enough to bring the ions close enough together. The ions can then fuse, causing a release of energy. In the sun, massive gravitational forces create the right conditions for fusion. But on Earth, they are much harder to achieve. As you can see in this figure, the tokamak consists of a torus-shaped magnetic chamber. A series of coils are evenly placed around the torus-shaped reactor, which helps in containing the plasma and therefore controlling the fusion reaction. Inside a tokamak, the energy produced through the fusion of atoms is absorbed as heat in the walls of the vessel. Like a conventional power plant, a fusion power plant uses this heat to produce steam and then electricity by way of turbines and generators. We currently get the majority of our energy requirements from fossil fuels and nuclear fission. While there have been great strides made in renewable energy over the last decade, we are still heading for an energy shortage. Increasing urbanization and new technology like cryptocurrency are driving up power demands all over the world, and nuclear fusion could help keep the lights on. Fusion could potentially add massive amounts of power to the existing grids. However, for realizing the potential of fusion energy, a lot depends on the International Thermonuclear Experimental Reactor being built in southern France, which is expected to be the world's largest fusion reactor when it becomes operational in 2035. After the International Space Station, the ITR is the largest human endeavor, which includes the United States, Russia, South Korea, Japan, China, India, and the European Union. India could be a dark horse in this pursuit, as it has a major role in the ITR. Scientists from the Institute of Plasma Research in Ahmedabad are guiding the industrial production of the ITR's critical components like the in-wall shielding, cooling water system, and cryogenics. In fact, the superstructure for the reactor's main equipment, where a vacuum is maintained to help cool the plasma, is made by Larsen and Toubro. Since building its first tokamak, India has made remarkable progress in fusion research and operates an advanced, steady-state superconducting tokamak, which overcomes the limitations of conventional tokamaks in heating plasma. Only a few countries have developed these next-generation steady-state superconducting tokamak. The East, for instance, is a tokamak designed for steady-state operation, and the Chinese engineers who built it were all nurtured by the ITR program. India should take a leaf out of China's notebook and use its participation in the ITR to get a leg up on building an indigenous fusion reactor on the Indian soil in the next few decades.